Okay, at the moment we're using a list of strings to store our unique clean locations. And here obviously there's a potential performance issue here when we're doing a lot of move operations. And we have to check how bad this actual problem might be. One way of doing this is a test. I wouldn't call it a unit test, but it's like a unit test, and we can use this unit test to distinguish between good and bad solutions. So first of all, we need to create a new test in Robot Cleaner Tests. So we're going to add a new unit test here, although this isn't strictly speaking a unit test, and we're going to call it, we can call it reporter test. Because we're testing against the reporter class, reporter tests. Okay. And in this, we call unit test, we'll be actually doing some timing tests. We'll be doing some timings of our operation on the reporter class. So let's create a simple reporter. New simple reporter. And then we need to do some execution and do some time exercises. The timings we'll be doing here will be relative. If we look at a graph of algorithm efficiency, we can see that what we'd like to have is actually sort of n log n performance or n log n efficiency. Okay. And in n log n, this purple line, you can see that roughly when you got around 20 operations, 22, 23, it's gonna cost a relative time cost of about 100. Okay. And if we increase the number of operations to around 90, 91, 92, then it requires a relative time cost of around 600. So whatever time 20 operations takes, around 90 operations should take around 6 times as long as the time for 20 operations. And that's our efficiency goal. That's what we'd like to achieve, n log n performance. So we need to create a test here to test this. So under our range, we want to carry out 23 different move operations. Well, not move operations, we want to carry out the storage of 23 different unique locations. So we can create a loop here, a for loop, I++. Actually, we should be starting our loop from 0, but it's not important. And we're going to use the .NET stopwatch class here to do some timing. So if we create a timer using the stopwatch class, stopwatch, start new. And then we need to, inside our loop, we need to be registering some unique locations. So we'll call the reporter.register new position, and yeah, we can call this new position. Actually, we might need an initial position to start from then. So let's create some sort of start position here, location, start position, and yeah, we can give it a new location. Just I guess 0, 0 is fine for the test. And then we're going to do a simple case here. So we're just going to move the robot by 1 each time and report the new cleaned location. So let's create another location, which is a new location, new position. And that can use the original actually no, you know what we'll just have one variable which we call current position. And we can give that current position. The new position will be the old current position X. If we move 1 north, then the new current position will be the old current position Y plus 1. Right, so we've updated our position, and we have to inform the reporter, which will check if this is a unique location and register that new unique location. So we do this 22 times, and at the end of this, we then need to check the how much time it's taken. So we can check the elapsed time, but actually check. Yeah, we can get. We need to actually stop our timer as well. We forgot to do that. So let's just stop our stopwatch. Okay, so we have a way of measuring how we register unique locations 22 times. So we have times for that, and we perhaps need to do the same again, except this time we're going to do it for around 90, well maybe 91, 92 cases. Yeah, and 90. So we'll just copy our loop. We need to start our timer again. Alright, so now we've got the elapsed time for the 90 case, the larger case. And then we should do some sort of assertion here. Now since it's n log n, we can see it's 600, and so the larger case should take around six times the amount of time that the smaller case takes. So we can assert, yeah, it's true that the elapsed time for the large case, elapsed time for the smaller case, elapsed 23, if we call that elapsed 23 cases, that should be less than, sorry, the elapsed time for the larger case should be less than the elapsed time for the smaller case times, yeah, we can be generous, we can say 8 as our upper limit of the performance loss we're willing to accept. So, yeah, we set that to milliseconds. That's fine, we could use ticks as well, probably actually. Okay, we've got 92 cases and 91 cases and 22 cases. So let's run that test to see how it goes. Okay, it's failed, but we can't see. It would probably be useful if, when the test fails, we get some sort of message showing us the actual elapsed times. So let's add a string message to our assert statement, so we can have a bit more information about what's going on. And we want to print out here the elapsed times for both the small case and the large case. So, yep. And here the small case has already been multiplied by 8. So if we run our test again. Aha, they're both reporting 0. Okay, probably not actually 0. It's probably just it's happening so fast. We probably need to increase the time it takes. We could do this by increasing the size of our loops. Yeah, so if we go 230, 920 as the upper limit. And if we rerun our tests again now, maybe we'll see some real times. Okay, almost there. Where the large case now is actually giving measurable times. But the smaller case isn't. So we perhaps should increase everything again. We can go up 1 factor more. So 2300, 9200, let's run that exam. And we don't need to be very exact here, just roughly want to. Okay, we failed. And here we can see that the larger case is actually 3 times 8 times the smaller case timing. So it's 24 times. So we can see from our graph that the larger case is actually, instead of taking 6 times as much it's actually taken, well, 24 times as much. So we're way up in the graph. Okay. So we need a much more efficient way of registering new unique clean locations. And one possible we should look at here was our next algorithm of choice, which was some sort of binary tree. And if we're going to implement a binary tree of coordinates, well, the first thing is we probably need some way of comparing coordinates. You know, we need a less than, and where this coordinate is less than the other coordinate. So we should probably implement iCompare. Okay, but we can always, as always, we start off with a test. We'll go to our location and location tests here, and we'll add a new location test so we can use to check our comparisons. We can actually do a comparison between coordinates. So let's do a compare location test. What do we begin with? We can start with something simple. We could do perhaps our bottom left and top right coordinates. Or actually, well, I guess it's x and y here, so perhaps we should do something like left for x, left and right. Let me see, the names aren't really important, but let's go with small. Yeah, we're just actually comparing a small x against a coordinate with a large x. So we're saying it doesn't really matter what the y is, and that should return, yeah, sure that the small x is less than the large x coordinate. Yep. So we need two locations. We need in our arrangement section. So we have location 1, which has a small x coordinate, 100. And we have another location 2, which has a bigger x component, 200. And then we're actually just need to assert that location 1 is less than location 2. Yeah, that's actually semantically. We haven't implemented anything yet, but semantically we just want to say that it's true that location 1 is less than location 2. Right. And obviously this test isn't going to work because we haven't built any comparison operator. So to work here. So to get our test to run, we're obviously going to have to fix that. Built in our iCompare operator. So if we go to our location class and implement our comparison operator, so we can inherit the or implement the iComparable interface T, and we're going to compare locations. Okay, well, we would say one location. If the x's are the same, then the y's decide if they're less than or greater than. So if this x is the same as other x, then we compare this y with the other y. And less than here returns -1, greater than returns 1, and the same returns 0. And if they're not equal to each other, then we just compare the x component of the coordinate. Okay, so now we've implemented iCompare. So now we can go back and change our test so that it actually works. We should have a comparison operator now. So if we've got location 1, compared to location 1, it should be less than location 2, so it should return a -1. And let's just change this to an r equal assert. We can set in our -1 value. Thanks, it looks a bit more obvious. Okay. If we run that test. Okay, we can still see that it's just our algorithm efficiency test is failing. So our comparison test here works. Oh, actually, we can see that our efficiency algorithm worked as well there, which is it's a bad type of test where it sometimes works. But we can fix that later on, so we don't need to worry about it. Okay, so let's add some more comparison tests. Let's check the reverse. If we try a large x against a smaller x, so location 1 should be larger than location 2 and the comparison should return a value of 1. So let's set x on location 1 to 200 and y to 100. Yeah, location x on location 2 to 100. And they've got this, even though the location 2's got a much larger y, it shouldn't make any difference here. We're still going to return a +1 value. So let's run that test. Yes, and the comparison test works. And actually, as I said before, even the efficiency test works, which is not good. Okay, so let's see what happens when they've got the same x but different y. So we've got a large y versus a small y, right? And okay, large y, small y, and that should also return 1. Right, and we're still just failing the algorithm efficiency, so the comparison test works. That's fine. Okay, and like I said, we will get back to the efficiency test once we change the algorithm, so we don't need to worry about that just now. Should we add any more tests? Yes, I think we need one more, actually, at least one more obvious case, and that's we want to compare what happens when we've got a result which gives -1, a result which gives +1. What happens when they're exactly the same? So we've got the same x and y, yep, and that should return that they are the same. And the comparison result therefore should be 0. So if we give these both the same x, y, let's check if they return 0. And they do. That's great. So all our comparison tests are working. It's fine. Okay, now that we've implemented comparison, we can implement our, binary tree or binary tree-like structure and see if we can get better performance. So if we go to our reporter, I'm actually not going to implement my own binary tree. I'm just going to use there are similar structures in .NET already, which we can already built. So if we use a private, we're going to use a sorted set of type location. Because sorted sets give roughly n log n performance for, well, it has a number of advantages. First of all, we get a n log n performance for insert and finding, and also a sorted set doesn't add an object if the object is already there in the set, so we don't need to test if it contains that location or not. So the actual count of the sorted set is always the number of unique locations visited. So we have that, and then we don't need to do anything here. We just need to add our position. And again, we return the count. Yep. So if we rebuild that and run our tests, and now even on our performance test, we should call this run robot some cases and many cases in log n performance. Okay. Okay, now we've implemented our storage, we've implemented our movements, we've implemented our reporting. So now we can actually do a proper test. And if we grab our robot test here, run robots, we'd say box command set, box move command set, and number of locations is correct. Okay, and the movements we are going to do here, we're going to start off with 0, 0. Then we're going to move up to 0, 7 with an N7 command, followed by an East 7 command, followed by a South 7 command, followed by a West 7 command, which should give us a total of 28 locations. Okay, so we'll create our test around this scenario. So our starting position here would be 0, 0. We will have North 7, East 7, South 7, and West 7. Total number of commands is 4. And we will create a reporter, which will be a simple reporter. Which we will submit. We can give it a bound here. The bottom bound is 0, 0, and the top corner is 7, 7. Then we execute our commands, and we should also create a report. And the report should say cleaned 28. Okay. Okay, let's run our test. Okay, we've got a failure. It says we expected to clean 28, but we've only cleaned 7. So let's perhaps debug our unit test and see what's going wrong here. Okay, we create the command factory and we're adding inputs here. And let's just check the command set we get back. We've got 4 commands, looks good. And we've got 4 moving commands. What are they? We've got 4 moving commands. North 7. Ah, okay, here we can see the problem. All the commands are north 7. So there's something about adding an input. It's not going correctly. Command set add parse movement command. Ah, okay, here we go. Here we see the problem. All the directions are north. Should be south. Should be east. It should be west. Okay, if we go back to our robot tests and rerun. Okay, now it's 28. Great, our scenario works. So now we're pretty much ready to try it in our client. If we go back to our client, here we've got our command factory where we're putting our inputs. Here we need to execute a robot, so we should create a robot here. Okay, there's no robot, probably is an internal, we need to make that public. Let's do this. Let's call him Robbie the robot, why not? We'll give it a command factory to get inputs. Command factory dot. Okay, we need to change that from internal to public. Yep, go back to our program, command factory dot get command set. And we need a reporter, so let's build a new reporter here as well. On the bottom left we can say new location 00, new location 77. Okay. robot, and here we're going to give it the number of 16. So here we console dot write line Robbie dot print report must be also internal. You notice I'm very conservative about what I make available. Only release things when it's absolutely necessary. Okay, let's see if we can build that. Okay, it runs. So if we go to our robot test, we've got a good command set here. We can test this now. Okay, we've got to give our command 4. Start position is 0, 0. First command is N7. Next command is East 7. This command is South 7. And last command is West 7. Now we have cleaned 28. Okay, so our solution works. I'll probably go back and implement a lot more unit tests just to check boundary conditions, but basically we think we've solved the problem as was given. Okay, thank you very much. Hope you enjoyed it.